Okay, here we go. We're going to talk a little bit about probability and doing some analysis of the data we've already collected. The first type we're going to do is called exploratory data analysis. We're going to do a multivariate analysis, see if we can pinpoint where the variation is coming from. And then we're going to do correlation and regression modeling. And finally, we're going to do some hypothesis testing. We'll get into the details in the PowerPoint. Now, variation can occur almost any place at any time, or it can be varied by time. For example, if we're talking about steel plates, it can be vary from where you'd measure it within that plate. It can vary from piece to piece, or it could just vary from hour to hour. Now, let's imagine that we have a wafer, and measuring the thickness of that wafer and how thick it is important. So if you look at these things, what we got are the green lines that represents the total variation. Within that green line, you'll see some little red squares that represents the variation on that location along that side. And finally, we have the blue line that represents the variation from wafer to wafer. We're talking about the average. And again, we're also trending this over time. You can see that it's actually starting to vary quite a bit as we go through time. It's starting to increase the size of the wafer. Now, knowing this, we can look at that and say, well, where's the variation? Is it positional, those little red dots? Is it from piece to piece, those blue dots? Is it time related? We look at the slope of the line from wafer to wafer, and we can find exactly where the excess variation is. If we don't have variation, well, we don't fix it, right? We just let it go. So we want to know where the variation is coming from, and we're not fixing a problem that doesn't exist. Again, this is just another way of saying where the variation is coming from: positional, cyclical, and temporal. Okay, we can do that from piece to piece or from batch to batch. All right, for the Greenbelt, we're going to talk about regression analysis. And what we're going to do is use a scatter plot. If you go to asq.org, they've got a scatter plot program. Excel also does a nice job of this. And what it does basically does plot one variable against another. So in this case, we're applying speed against distance. So as we speed up, how far do we go? And then you see that red line, that's called the trend line, or that's the regression line. We'll talk about that some more. Now, if you look at this formula, this is how you figure out the regression line. It's basically the slope of a line. Y is equal to a times some slope times the x coordinate. And if you look at the B equation, how you figure out that slope, right? And the intercept is computed as such. A lot of work. We're not going to do this, but this is the formula you would use. We're going to let the computer take care of this. Fortunately, we have this thing called Excel. If you don't have Excel, let me know. There are other ways of doing this, other computer programs, so I'll share it. But if you have Excel, this way I want you to do it. What you do is you design a scatter plot between the two variables. In this case, we got sales over time. We add a trend line. Right-click on the mouse, and I want you to format the trend line. So this is how we're going to do it. If you look at this is the example. We got a scatter plot of sales plotted against years. And if you right-click on Excel, this is an Excel spreadsheet, right-click on the chart, this format trend line will pop up. You want to click on that. Okay, this will pop up. This is the box that will pop up. You want to click on the linear, on the trend regression type, trend line options, linear, where the little green dot is. And then you want to come down. You see where it says display equation on the chart and display R squared value on the chart. Click on those also. Okay, the trend line will be put on the chart. That's that dashed arrow line. And then you want to see, I'm circled on this graph. You see that y is equal to 62.424x minus 123.427. R squared is equal to 0.7781. Those are the result of those last two clicks. Now, what I want to point out is that y equation, that is a linear regression line. And we'll talk about what the r squared means here in a second. Okay, that r will indicate the strength of our relationship to the two variables. That's called a correlation coefficient. A perfect correlation would be r equal to 1. That means as our x value goes up, y value will go up proportionally the same. R value of -1 is just as good also. That means for every time the x value goes down or up, the y value goes down. It's a negative correlation. If you see an r equal to 0, there's no evidence of any linear relationship. So that doesn't mean there's not a relationship, it's just not linear. Okay. This is just the equation. This is how we used to do it before we had computers. All of us guys that are over about 45 or so, we all had to do it one time by hand like this. Now if you look at that r squared term, let's talk about that. We just showed what r is. That's basically the correlation. If I square that, I get this r squared term. That's the calculation I'm interested in. Why? Here's why. R squared is actually called the coefficient of determination. A guy named Pearson was really a smart guy. Came up with this. So that number we had, that 77 that's actually telling me about 78% of my variation in sales can be explained by the time we've been in business. So that means that there's 22% of the variation I can't explain, right? So all you do is take the correlation and square it. And that gives me the coefficient of determination. And it says I can explain 78% of the variation by that bottom variable. Well, what if it's not linear? You know, when you right-clicked on those on that scatter diagram, this popped up. These other regression types, these are all called link functions. So what you can do is click on those, and I'd recommend that you play with it a bit. And what you do then is you just see which one best fits. And then you want to click on display the equation on the chart and the r squared, right? So what you're looking for is the one with the highest r squared to match. We're not going to go over that in the Greenbelt course, but it's out there for you if you want to try it. The higher the r squared, the better your equation is at predicting your results. Now we're going to talk a little bit about p-value. Technically, it's defined as the probability of attaining a result to or more extreme than what was actually observed when the null hypothesis is true. In English, when you get a p-value, that's actually the probability that what you're seeing is a result of random chance. So if I get a p-value of 10.10 or 10%, that's telling me there's a 10% probability that that's just random chance that's happening. Really nothing special going on. If I get a 90% chance, it tells me this more than likely it's just random chance. A good rule of thumb is p is greater than 5%. You generally don't take that as being proven because there's a good chance, more than 1 in 20 chance that was just random variation. If it goes from 1 to 5%, we call that statistically significant. And we would probably pull the trigger on that one. But if it's less than 0.1%, man, it's probably not random chance at all. Something's actually happening. Now, anytime you start talking about hypothesis testing, there's a chance that we're just going to make the wrong decision because we're going to make this decision based on sampling. So if I were to make the decision, I'm looking on the right there, decision based on the p-value, and I don't reject the null hypothesis. In other words, I say there's no difference. I would like for the reality to show that there is no difference. On the same token, if I say there is a difference, I would like for reality to also show no difference. However, there is a chance I'll say there is a difference when in fact there is no difference. That's called the alpha type error. That's also called a type 1 error. In other words, I made a mistake based on that. And then there's the other type where I call no difference. In fact, there is a difference. That's called a beta type error or a type 2 error. These things happen. And we can set those alpha and betas at whatever I want. Generally for industry, it's about 5%. It doesn't work with a drug company. They got to do better than 0.1%, so they got to do quite a bit of testing. Again, we're talking about probability. So remember this curve from a long time ago, the bell curve, where I had the 68% plus or minus 1 standard deviation, 95%, and 99.73 plus or minus 3 standard deviations. This is what we're talking about by the p-value. The smaller the p-value, the less chance that we're seeing random variation. And a rule of thumb is p if low, HO must go. In other words, the null hypothesis gets rejected. These are the 4 type of hypothesis tests that we'll talk about in the Greenbelt. I'm not even going to try to do this with the PowerPoint. If you have questions, I'll do a video. There's some videos out there already. If I have variable data, in other words, stuff that can be like 1.004578, then I can start doing these 2 tests. One's a z-test, the other's a t-test. The z-test focuses when you're looking at the whole population. T-test is generally based on sampling. And there's a nice little video I put on that. So the other type is discrete data. There's binomial. This is go, no go. Heads, tails, pass, fail. First pass yields is an example of this. And that's discrete. You can't have one half pass. It's all the way passed. The other one's Poisson. And this is a number of defects, number of possibilities of on a roll of a dice, or 6. I can't have a 6.2 on a dice. I can't have half a defect on the car. So these are discrete data. You cannot divide them. They're there. You count them as go, no go. Defects, you just can't divide it any finer. Now, a couple things you need to know. Remember, very first class we had, we said the 2 most important things about any set of data is the center and also the spread. How much does it vary? So if you want to do a point estimate, we're going to do the average. But we can't be exactly sure because we're dealing with sampling and we're doing probability. So we get this thing, it's called x bar, which is our average, plus or minus z, and watch the video on how to do a z-score times the standard deviation by the square root of the sample size. And what that'll do is it'll give me an interval, kind of a confidence interval. You've seen this on polling, and plus or 44% plus or minus 3.4%. That's what they're doing here. They're just taking a variable data, and they're doing a point estimate of what the average is. The other one is proportions, and then I just take, well, I've got a first pass yield of 98.7. I do a test, I get a 96.2, and I can do the same thing. I could take that 90, the new average, take it times the z-score, and what you're seeing there, that p times 1 minus p divided by n, I'll take the square root of that. That is the standard deviation for defects or for discrete data. Again, I'll post some Excel spreadsheets. I'll do some videos. You're not going to learn this watching this PowerPoint. You just can't. I honestly believe that anytime you're dealing with math, science, technology, you need to see it be worked out to understand it. So ask questions, okay? I encourage you to ask questions. And look in the discussion. There's going to be a lot of discussion, I hope. Thanks.